Good morning and welcome to our lesson today. We want to discuss the turning effect of force. Remember, we have been navigating through the effect of force as well as what force can do for us. And just to remind you, we have about 4 effects of force. One is that it can change shape or distort an object. Number 2 is that force can change direction. Force can also stop motion, and force can as well trigger motion. Force can trigger motion, it can stop the same, can change direction, or even the shape of an object. Now, today we are interested in how force can be able to change the direction of an object, an effect we are going to call the turning effect of force. Now, probably you might ask yourself, why should we say that force can turn an object? I want you to think about a few activities. For example, when you are turning off a water tap, when you are turning off a water tap, when you are opening or closing a door, when probably you are steering a car, when you are loosening or even tightening a nut. All these are activities that will involve the turning effect of force. Now, if we say that something is turning, it has to be at an angle. For example, if force is to turn something, there has to be a point of support through which that effect is supposed to be felt. For example, let us consider a meter rule that is supported at the center, like this. A meter rule that is supported by a fulcrum at the center. Now, if you apply some force on this side at whatever point, and with reference to your fulcrum, this force is going to turn the meter rule about the fulcrum in the clockwise direction. Suppose the same is applied on the other side. Suppose the same is applied on this side. Again, you will realize that the meter rule is going to be turned about the fulcrum in the anti-clockwise direction, in this direction. So, in both cases, of course, the force has to have some magnitude, and again, it has the direction of effect of the same. And bearing in mind that force in itself is a vector, force is a vector quantity. It means we have to take care of the direction. We have to take care of the direction as well as the magnitude. Magnitude, in other words, is the size of the force, and then the direction of action of the force is equally important. Now, let us go a step further and discuss what we call moments of a force. Moment of a force. Moment of a force. And here I want us to consider our simple diagram again. Where we have a meter rule supported, say, at the center. And then we have, at the center, we have the 50 centimeters mark. Then probably at some point, for example, at the 80 centimeters mark, we have a force acting downwards. Now, there is this distance from the fulcrum. We are going to call D meters or centimeters, but here it is always important to work with SI units. Now, this distance is the perpendicular distance between the point of support and the line of action of the force. The line of action of the force. Therefore, we have this perpendicular distance. Let us say that the magnitude is X newtons. The magnitude of our force is X newtons, and the force is acting at a point D centimeters from the fulcrum. Now, the product of force and the perpendicular distance between the pivot or the fulcrum, if you may, and the line of action, of the force is what we call moment of the force. So here, for example, we are going to take our D centimeters, change it to meters by dividing by 100, then multiply by the magnitude of the force, which is X newtons, and the product should result in the moment of the same. Let us take an example or two. Now the question reads, a pupil applies a force of 10 newtons to the handles of a door, which is 0.8 meters from the hinges. Calculate the moment of the force. Now we have said that moment is given by force multiplied by perpendicular. Distance. In our case here, we have a force of 10 newtons acting about 0.8 meters from the point of support, and therefore our moment is going to be 8 Newton meters. 8 Newton meters. It is good to note the units of moment, of force, are actually Newton meters. Now, let us look at another example. Now let us assume a setup of this nature, and the pivot is placed somewhere here on our seesaw. Then at a distance 1.2 meters from the pivot is where the weight of the pet dog is acting. Now, the pet is 10 kgs by mass, so we multiply by 10, so that now the weight is about 100 newtons. Now, we want the moment of that force due to the mass of our pet dog. And again, we consider moment being equal to mass to force multiplied by distance. In our case here, we have a distance of 1.2 meters, and the force is about 100 newtons. Therefore, the moment will be 120 Newton meters. 120 Newton meters. I will look at one last example. Example 3. Now here we have an interesting question where we are required to get the moment due to our force 6 newtons about this point, about 0, or about the point O. But we said that moment is the product of force and perpendicular distance perpendicular distance between the line of action. In our case, the line of action of our force is this one. It will act along this line. Therefore, we are going to require the size of this distance because it is the one that is actually perpendicular to the line of action of our force. Now, if we take our diagram to be a triangle, then we can apply Pythagoras theorem so that we can come up with this distance that we need in our calculation of moment, so that we will say 5 squared will be equal to 3 squared plus, say, d squared. Therefore, 25 should be equal to the sum of 9 and d squared, giving our d squared as 16, and therefore d is the positive square root, which is actually 4. Now, with this distance, we now can take our force, the magnitude of our force, which is 6 newtons, and we multiply by our distance, which is 4 meters, so that now our moment can be taken to be 24 Newton meters. Now, let me give you some questions that you should try and answer in the course of your study. Number 1, give 4 effects of force as a vector. You should give, or you list down, the 4 effects that we have talked about of force as a vector. In the beginning, we tried to recap the same, and we said that force can change direction and even the shape of an object. It can trigger motion as well as stop the same. Number 2, you try and define moment of a force. Try and define moment of a force. And number 3, you can work out the following question. When you define moment, indicate the SI units. Indicate the SI units of moment of force. Number 3, you can try and work out this question. A force of 60 newtons is acting at a distance of 20 centimeters from the point of support. Now we want to try and calculate the moment in the course of our revision. Try and work out that question in the course of your revision. And just a hint, your answer should be 12 Newton meters. If you are able to obtain 12 Newton meters, then you will be on the right track. Let us advance and look at the principle of moment. And the principle of moment is important in order for us to establish the point of balance or the equilibrium of a setup in science. Now, it governs the relationship between the forces that act on an object with reference to their moments. Now, let us state the principle first, and it states that for a system at, just use at equilibrium, or for a system to balance, clockwise moment should be equal to anti-clockwise moment. Clockwise moment should be equal to anti-clockwise moment. Let us consider a general figure. Place the pivot somewhere at the center and put some two forces, F1 and F2, on either sides of the pivot. Now, each one of these forces is going to have its own moment about the pivot. Now, but there is also that factor of the direction of action of the force. For example, if we applied only F2 and we left the other side without a force acting on it, then F2 tends to turn our system in the clockwise direction, like this. If only F2 was to act on this setup, then it would turn in the clockwise direction. How about F1? If we withdrew F2 and we left F1 to act on the system alone, then it would move, or it would turn in the other direction. Now it would turn in this direction. Now this one is what we call the clockwise direction. And this one is the anti-clockwise direction. Anti-clockwise direction. Now, we have the clockwise and we have the anti-clockwise directions respectively. Now, the moment that turns a system in the clockwise direction is what we call the clockwise moment. Now, in the same case, the moment that will turn our system in the anti-clockwise direction is what we call anti-clockwise moment. Let us note that down. That clockwise moment clockwise moment is movement that turns a system in the clockwise direction. Now the reverse is true for the anti-clockwise. For the anti-clockwise moment, it turns a system in anti-clockwise direction. Anti-clockwise direction. Now, but we are saying that for our principle to hold, these two have to balance all other for the system to remain at equilibrium so that it doesn't turn in any direction. Then the two, the clockwise and the anti-clockwise, have to balance. Now let us look at a numeric example to that effect. Now, our meter rule is balanced by three forces like the way we have been shown by the diagram. Now we want to calculate the size of force F. We want to calculate the size of force F. Now, let us consider clockwise moment. And clockwise moment is given by those forces that act to the left side of our meter rule, that is force F, and the force that is 2.0 newtons. So for force F, the perpendicular distance between the fulcrum and its line of action is actually 66 minus 50, which gives us 16 centimeters. For the force whose magnitude is 2.0, we have 90. This direction, this distance here should be 90 minus 50. So that gives us a distance of 40 centimeters. Now, if we change the same to meters, 16 will be 0.16 meters, 40 will be 0.4 meters. Now, the clockwise moment therefore will be given by moment due to the first force, which we want to calculate, which is force times its distance, which is 0.16 meters. This one we add to the moment of the second force, which is given by 2.0 multiplied by 0.4, which is the distance. Now, this will be 0.16 F, then we add to 0.08 Newton meters. Now, the anti-clockwise direction will give us anti-clockwise moment as the distance from the line of action to the fulcrum, which will be 50 minus 20, giving us 30 centimeters, which is equivalent to 0.3 meters. So, anti-clockwise moment will be given by the product of 4.8 and 0.3 meters. 0.3 giving us 1.44 Newton meters. Now, but from the principle that we have been studying, the principle of moment, clockwise moment should be equal to anti-clockwise moment. Therefore, we take the moments and equate them so that now we have 0.16 F plus 0.08 Newton meters being equal to 1.44 Newton meters. Let us collect the right terms so that 0.16 F is going to be given by 1.44 minus 0.08. These are Newton meters. So that now our 0.16 F will be equal to 0.64 Newton meters. Then we can divide by 0.16, can divide the other side by 0.16. We can cancel by 8, 2, by 8, 8, then by 2, by 2, 4, so that F, implying that F is equal to 4. Is it? Yeah, 4.0 newtons. F is 4.0 newtons. Therefore, what we do is that we resolve the distances. Then we calculate the clockwise moment and clockwise moment individually. Then you take care of all the forces in the setup, after which we are supposed to equate the moments so that we can collect the like terms and finally calculate our function of interest. We can calculate our function of interest. Let us take another example too. that we have the following setup, where a force of 1.5 kgs translating to 150 newtons balances a meter rule when another one, which is F, is placed at 100 centimeters mark. We are interested in the size of the force acting at the 100 centimeters mark, bearing in mind that we have our fulcrum placed at the 20 centimeters mark. Now, let us start by calculating the clockwise moment, which is going to be given by the force F, which we want to calculate, and the perpendicular distance from the point of support to its line of action multiplied together. Then we will also have this distance being the perpendicular distance between the fulcrum at the point of support of our force of 150 newtons, which is going to be 20 minus 0, giving us 20 centimeters. Now the clockwise moment is given by force multiplied by the distance, which is 80 over 100. These ones are Newton meters, giving us 0.8 F Newton meters. And clockwise moment is given by 150 newtons multiplied by 20 over 100 to make them meters. And this one is going to give us 30 Newton meters. 30 Newton meters. But for the system to balance, clockwise moment should be equal to anti-clockwise moment, implying that this implies that 0.8 F is equal to 30 Newton meters. Then we can divide throughout by 0.8. The other side we can divide by 0.8, which will be equal to 300 divided by 8. And our force F will be 37.5 newtons. Again, we started by calculating the clockwise moment, which is the moment due to forces which would turn our system in the clockwise direction. That one we calculated individually. We then went to the anti-clockwise moment given by forces that would turn our system in the anti-clockwise direction. Then we must equate the two we must equate the two for our system to be in equilibrium. The principle requires us to equate the two moments so that we can be able to resolve our force F, which is the force that we wanted to calculate. I will look at one very last example. The question reads, calculate the force F which would help to place the figure below at equilibrium. Then we have our F here. We have 20 newtons at the 45 centimeters mark, and then at 75 is where we have another one, 10 newtons. 10 newtons. Again, we start by asking ourselves, in which direction will the forces that we have turn our system? In what direction, or in which direction will the forces that we have turn our system? Now, for the force F, if it was to act on our system alone, it would turn it in anti-clockwise direction, and the other two would turn our system in the clockwise direction. Therefore, let us now resolve the moments. Let us resolve the moments. Clockwise moment will be given by this distance here, 45 minus 30, giving us 15 centimeters. We also have another one, this one here, 75 minus 30, giving us 45 centimeters. Therefore, clockwise moment will be given by 20 multiplied by 15 over 100. We add to 10 multiplied by 45 over 100 meters. This one here gives us 3 Newton meters, then plus 4.5 Newton meters. So our clockwise moment is going to be 7.5 Newton meters. Now, how about the anti-clockwise moment? We consider this distance here, which will be 30 minus 10, giving us 20 centimeters. Therefore, anti-clockwise moment is given by 20 over 100 multiplied by F, which we want to calculate. so that we now have 0.2 F. But from the principle of moment, we can be in a position to equate anti-clockwise moment to the clockwise moment, so that 7.5 Newton meters will be equal to 0.2 F. Therefore, we divide both sides by 0.2 by 0.2, so that our F is 37.5 Newton meters. Again, just a reminder, start by asking yourself which of the forces on the setup would turn your system in the clockwise moment, in the clockwise direction. Those very forces should give you the clockwise moment. And in our case, we had a force of 20 newtons and another one of 10, which would turn our system in the clockwise direction. We resolved the moments by multiplying by the perpendicular distance. Very important to remember that it's the perpendicular distance between the point of support and the line of action. Note that force does not act at a point. It acts along a line in its own direction because it's a vector. Now again, the anti-clockwise moment will equally be given by those forces that would turn our system in the anti-clockwise direction if they were to be left to act on the system alone. Now after that, we now equate the two moments from the principle that we have just studied, so that we can collect the like terms and come up with the quantity we seek to calculate. Again, I will want to give some questions which you should consider in the course of your revision. And question number 1 requires you to state the principle of moment state the principle of moment. Number 2 is to distinguish between clockwise moment and anti-clockwise moment. The last question, you calculate, work it out, the question reads, a uniform rule is pivoted at the center, then if a mass of 100 grams is placed at the 25 centimeters mark, you are required to calculate the distance or the mark at which another mass of 50 grams should be placed so that the system stands at equilibrium. That's about all for today. Next time we meet, we shall look at parallel forces. Thank you.